show you the final model. Basically, this is the schematic of the EPC design. It's a full bridge. What I did in this video is to design the final model and make it like a final video, because it's quite difficult to show step-by-step process. But pretty much the concept I've shown in the previous videos, how to move the winding, how to cut the winding, how to stack the windings. In this video I'll show the final model, how it looks like. But one thing I want to make clear is the positive turns and the negative turns. Let's say you have a DC bus voltage here. So this MOSFET Q1 and Q2 conduct. So the current flows like this here and goes through here back to the DC bus through this FET. At that time these two are off. When current flows like this, the positive turn is this specific loop where these MOSFETs turn on and these MOSFETs turn on. So this is the positive, and during the negative these two MOSFETs turn on and this loop is on. This is the negative loop, this is the negative loop. In the presentation they have marked this is positive turn because it's going from the ground side to the V out. It's a positive turn. They have written this one wrong. This should be positive and this one should be negative turns. And the other point is, in the previous videos I was combining it as a single layer, which is wrong. I'll show you that it's better to take it as a split winding, just one winding here and one winding here, third winding and fourth winding. So there are 4 turns on the primary. This is one turn, this is the second turn, this is the third turn, this is the fourth turn. These are the 4 primary. But the 4 turns have another 4 turns in parallel so that the current conduction is better. Similarly, there is only one turn on the secondary, but you have several secondaries here because they are in parallel. That is one point, and I modeled everything exactly as it is shown here. This is half winding, this is half as the secondary, and for the primary as well I modeled it exactly like a split square here, split square here, something like this. This is round here, but I made it like a square, much easier. And you don't need to model this one because they have already given the CMXY coefficients. Let me see, view datasheet and ML91S. All I did is just enter these coefficients here. You see, either you can enter these coefficients K, alpha and beta in the core setup. It looks something like this. Properties, and it looks like this. Basically I put permeability 900, power farad. These numbers I got it from here. Basically this is kilowatt per meter cube, so kilo is like 1000, so I multiplied this with 1000 and I entered that number. X is 1.938 and alpha is 3.33. That's all you need to do. That is the core. And the winding, fit all, I'll click on trimetric. And In the previous videos, I had a region which I drew as a rectangle. I deleted that and I added this specific region. Once you click on this region, you can just draw it and adjust the padding. I just put it as 150, 150, 150, 150, and make sure the core and everything is inside this. Let me just hide this one. Copper, I put I'll just select these, show them, orient in top Z, and this is how I split it. Basically, previously I had only one primary, so what I did, I just drew a rectangle and then use the boolean function to cut this one. But since this complete thing will still show as primary here, all I did was modular boolean separate bodies. This will get activated. That's when you can split it and add the coil terminal and show it as primary 3 right, left and right. So this is the left, this is the right, and the coil terminal is somewhere under the sheets. Left coil terminal, right coil terminal, and under the excitation, left is I just model this current direction exactly as shown here in the presentation, where the winding direction is. This is going down, this is going up. I modeled it exactly like that. Right, if you see, it's going up. I'll just quickly show how it looks like. A solution exists. Okay, I don't want to show it over here. So once you had the complete primary, you can add a rectangle and split this one, then click on boolean and separate bodies so that you can create the coil terminal for primary 3 and primary 3 right. Similarly, I did exactly everything, like you can go over it. Basically, it was a little tedious. I manually drew it, then you add the coil terminal, and then I put in the excitations as 0.5 PWL periodic, and I did not use the Maxwell circuit, the simpler inside this, to simulate the current. What I did, I actually cheated and I used Simplis. This is my favorite software, LT Spice and Simplis, much easier to use. I will share a GitHub folder where I have the EPC2071 model, and this is an open loop, just giving a 1 megahertz excitation. This is a ideal way of drawing a diode. So the current is flowing like this, and I named this as positive. This goes like V out in this direction, and over here as well it goes in this direction. This is the positive, and this side is the negative. S1 is negative, S1 is negative, whereas S2 and S2 is positive. So in the EPC, this on one single layer, there are negative, this is positive. As I said, they have typo here. This is positive turns. So the way they did it is, on one single layer, this is the positive layer and this is the positive layer. They put side by side, and they put negative layer S1 and S1 here as the negative layers on one negative layers. This is the negative, this is the positive. They kept side by side, and the primary is 1 here, 2 turn, 3 turn, and 4 turn. Much easier to model it like that. That is one thing. And I did run a simulation. You can actually download free version of this one and simulate it. Once you simulate, run schematic, it is perfectly ideal. You don't really need EPC, you can put ideal switches as well. And I put the spice model for this one as well. So you try to get the waveforms from here, the primary waveform and the secondary waveform, and I just put it in design datasets. Now there's one caveat here. Let me show you what that is. So this is operating at the resonant frequency 1 megahertz. You have 12 volt 83 amp. This is how the waveform looks like. Output is regulated at 12 volts, perfectly ideal. What I did is go stack all curves, and I saved this one primary. What I did, I do copy, right click, copy to clipboard graph data. Once I click the graph data, actually it's saving from 49.99 microsecond to 50 microsecond. So in the text file as well, once you copy it, right click paste, it will start from 48.99. Now if you try to put this in ANSYS, it will complain that it's not starting from 0. So what I did, I saved each and every primary. Let's say primary, I click copy to clipboard graph data and do a control V. I get the X and Y amplitudes. Let's see, just to show you. Copy to clipboard graph data. I just select primary. Okay. If I copy it, it will show something like this. This is how the data looks like. It will look something like this. The problem is it's starting from 49 microsecond. So 49 microsecond, which the ANSYS will complain. So what I did file and save as .tab file. Saved the file as .tab, and I asked ChatGPT to not change the Y value, only change the X value. That's all I told, and ChatGPT gave me the file. I just imported the file in ANSYS. So all I told ChatGPT is don't change the Y, only change this X to start from 0. To start from 0. That's how I did design data sets. This one I just said import, and I had the tab file. I just uploaded it here. That's how it looks like, I think. And positive, the reset, negative, I just put the files signals over here. So this half primary are in parallel. Properties, I did 0.5. I assumed equal current is flowing. This is the data set I already have under the design data sets. Secondary, all are in parallel. It's like one turn here. This is 2 turn. This is 2 turn. So 4 turns on the primary. 1 turn here, 1 turn here, 1 turn here, 1 turn here. But they have put several turns in parallel so that the secondary can conduct the current. So 2 1 1 2 1 1, and I just clearly followed what is shown in this one. What is shown in this one? What is shown in this one? clearly followed exactly these steps in creating the current direction, the coil terminal. That's how I did second min on the same layer actually. If I just do and show, yeah, this is 1, this is 2. Min means minus, and this is plus 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 minus minus minus, and that's how I did it. And what I did, coil terminal, I split 0.25, so all the current that is flowing through the minus, so there are 4 turns in parallel over here. There are, if you assume this is one leg of the transformer and everything from top to bottom is across this and this, so if you see secondary plus secondary plus secondary plus secondary plus, so they have 4 in parallel, 4 for a single turn across one transformer. They have 4 in parallel. This repeats over here as well. Let's assume this is one single leg. From top to bottom you have secondary plus, then there is secondary plus secondary. So if I put one turn here, I am putting 4 in parallel just for the current to so that the secondary can handle higher current. It's just one turn here, so you're putting 4 in parallel basically. That's the reason the current I divided by 1/4, that is 0.25. 0.25 property is 0.25, the negative current, and for the positive as well, properties I did 0.25. So each of this, if you look at it, plus, this is plus secondary 4 plus secondary 5 plus secondary 10 plus secondary 11 plus, so all 4 are in parallel, but it's only one turn. And shield as well, I just drew it. That's how I do it. And material, and under analysis setup I just put it 5. You can make it 25 nanoseconds, but I made it very fine because I'm running this on a server. Save fields, just click on here, and then I just added the results. I'm showing you the core. So once you plot the core, you just select the core and just rectangular report, rectangular plot, just select the loss as core loss and you just plot it. So over here I'm getting 71.72 milliwatt average loss. 0 to 1 microsecond, 1 to 2 I simulated only for certain amount of time. So what I did, trace characteristics, all the average I did from specified from, let's say, 2 microsecond to 3 microsecond. That's how I did it to plot this one. Now there is one thing I wanted to make clear is they are approximating, EPC is approximating this as 1 watt of loss in the core. 1 watt of loss happens at, this is the volume of the core, pi r square h times 2, because my core is this, pi r square h. To get the volume of this core, pi r square h, so 2 of them, then length, width and height of this one. This is the 12.2 times 36 times this one, 4.57 minus 1.57, that's like 2 or 3. That's this volume, and this volume is pi r square h, that's what I wrote it down, the volume, and the area is pi r square, so you get millimeter cube, millimeter square. So this is the formula, V is equal to N d phi dt. V is volt voltage, N is number of turns, A is area of core, dB dt. You're going from minus Bmax to plus Bmax in half the time period. So this is the formula for the Bmax. When I plot the voltage across the primary here, across the complete primary, this complete primary is minus 48 to plus 48. Over here it's minus 24 to plus 24, minus 24 to plus 24. So what is happening is so that's what I describe over here. V1 is one across half primary. So once you enter 24, because during the on time, during the half time period, the voltage across the transformer is 24. 10 power 6 is 1 over f, 1 megahertz is the switching frequency. That's why you get 10 power minus 6. Time, and this is just a factor, multiplication factor for millimeter square. So you have 4 here, number of turns is 2. Why do I put 2? Because I'm considering this as 1/2. You're considering this as one transformer, this as one transformer. So across this first leg you have 1 turn, 2 turn. So that's why you put 2 turn here. And 0.45 is this specific area of the core. So you get 66 millitesla. Now 66 millitesla in this data sheet for this one, 66 is around 10, 20, 30, 40, 50, 60. 60 is somewhere over here. Let's say it's like 100, 200, 300 at 1 megahertz, 300 kilowatt per meter cube. If you multiply that with the volume, 300 kilometer cube times this volume in meter cube, you get on left half of the core you are seeing 438 milliwatts. So right leg as well I'll see 0.438, and the total core loss is 0.876. This is how mathematically I believe EPC has done. But when I plot it, I'm seeing 438 millitesla only near the center leg. I'll show it to you in a moment. So I plotted the copper loss, which appears as 6.6 watts, and what they have shown or approximated EPC is I believe it's around 2.6 plus 2.1 is 4.7. So we are getting 6.6 in ANSYS. This is kind of agreeable. Core loss is pretty tiny because it's only 71 milliwatts. How can EPC show 1 watt and I am getting 71? So the CMXY, the Steinmetz equation or core loss equation, this core loss equation, if you look at it, it is alpha once you are at 1 megahertz. If you take a look at 100 kilohertz switching frequency, you take 300 millitesla as the saturation flux density. Once you are at 1 megahertz, you take like probably 30 millitesla. That's why the core loss as well, it goes only until 10, 20, 30, 40, 50, not more than that, because at that switching frequency you are operating at a very tiny little Bmax. So I'll show you what the Bmax is, but remember this alpha is bigger for the flux density versus the switching frequency. So this you are reducing, this you are increasing switching frequency. Keep that in mind. And I'll justify why I'm getting 71 millitesla. So I selected the core. You can look at previous videos. I select the core. Over here. Just do right click, select, and then select all, and then do a fields B, and then you plot on surface and click on done. Then check this time to 2 microsecond, and you'll see the B is like this. Let me orient in trimetric. So this is millitesla. If you want to change, modify, right click and modify scale, you can put 100 millitesla linear. So what I observe is here is where the flux density is much higher. Actually, it's almost like here it's around 88. Rest of it is very good actually. Here it's around 44. Here it's all much lower. Only during the center leg is where it's getting kind of higher Bmax. If you multiply this B, let me show you the loss on this one, then it will make much more sense. You see, if you multiply this 5.553 times 10 power 5 times the volume, which is 1, this is meter cube, so volume is around 1460, that is 1460 milli. Milli is 10 power 3, 10 power minus 9 meter cube times this is 553 10 power 5. How much is it? So if you multiply, it will come close to let me see how much is it, if I have the calculator. So this will come close to around 400 to 438. I was expecting that the core loss on this one will be much more distributed. It will be all yellow, but it appears that it is red here, yellow here. Rest of the places it's not even lossy. So you make sure when you're setting up, you make sure set eddy effects, this is all turned on, and Maxwell design settings, matrix computation, click on enable apparent, excitation, set eddy effects, set core loss only on the bottom and the top core. That's what I did. And this is the current density of the wire or the PCB, where it appears as if it's much like 5 amp, 6 amp to 10 amp per millimeter square, most of the places except for the center. Except for the center where it's much more red, that means it's kind of getting hot. And I approximated the way I drew these. It's not like 100% accurate, but just for a quick simulation, I had the current density plotted. So this is how it looks like, and core loss is 71 milliwatt. Copper loss is 6.63. Only at the center legs is where you have a higher loss.